When concepts are mastered, it is quite easy and short when solving for partial determinants. Welcome to Numerical Solutions to C Problems. The first problem includes Laplace Cofactor Expansion. Given matrix A, we are to figure out the second partial determinant. The Laplace Cofactor Expansion will be using the second column. And to focus on the second term, just cover the second element from the second column. By covering the second row and the second column, the second partial determinant then is computed as the scalar raised to the second row and second column. Then, this is multiplied by element 2, 2. For this example, it is positive 1. Then attach the determinant of the uncovered elements, which turns into a 3 by 3 size, where we can use Sarah's rule. So mirror the first two columns and start with the diagonals. The first has 3, 2, and 6 multiplied into 36. The second diagonal has 5 times 4 times 2 making 40. The next has 2 times 5 times 3 making 30. For the anti-diagonals, the first product includes 2, 2, and 2 making 8. The second anti-diagonal has 3, 4, and 3 making 36. The third product has 6, 5, and 5 giving 150. Add all the positives to make 106. All the negatives are also added to 194. The second partial determinant is then taken as 1 times 1 with the positives minus negatives, or 1 times 1 times 106 minus 194, simplified as 88. The second problem includes Chio'S pivotal condensation method for the determinant of matrix B, although it only requires the resulting 3 by 3 matrix. Using the method, the first rule is to look for an element equal to 1, then use it as a pivot element, which means cover the row and column of the element. For this example, the pivot element is at element 2, 2. The resulting determinant of B, then, is the scalar of negative 1 raised to the location of the pivot element, which is 2 plus 2. The remaining elements for the reduced matrix are placed in the determinant, and we are to subtract reflected factors. For element 1, 1, subtract negative 2 times 4, making the element 11. Element 2, 1 is subtracted by negative 2 times 2, making 10. The third one below is negative 4 minus negative 2 times 5, making 6. For the second column, there is negative 6 minus 5 times 4, resulting to negative 26. The one below it is subtracted by 5 times 2, making negative 11. The third element in the column is reduced by 5 times 5, giving negative 22. For the third column, the first element is 2 minus negative 1 times 4, bringing 6. The next element is subtracted by negative 1 times 2, making 5. The last one is 7 minus negative 1 times 5, which is 12. With positive 1 as a scalar, the reduced 3 by 3 matrix of B is shown. The next example involves Gbemi'S rule. And using matrix A, we are to look for the second partial determinant. Recall that the second partial determinant using this method includes columns 1, 3, 4, and 2. So from the original matrix, rotate columns 2, 3, and 4. Then, with the method, mirror the first three columns and continue with Sarah's rule. The first diagonal has 3 times negative 6 times 4 and another 4, giving negative 288. The second diagonal has 5 times negative 2 times negative 3 times 2, which is 60. The third ray has 2 times 1 times 5 times 3, giving 30. And the last diagonal has negative 2 times negative 4 times 2 times 6, resulting to 96. For the anti-diagonals, the first has 2 times 2 times negative 2 and another negative 2, bringing 16. The second anti-diagonal has elements 3, 4, 1, and 3 multiplied to get 36. The third includes 6 times negative 3 times negative 4 and 5, making 360. Then the last anti-diagonal has 4, 5, negative 6, and 2, giving negative 240. Now attach the alternating signs for each diagonal, which start with a positive. So, they are simplified as negative 414. For the anti-diagonals, the alternating signs start with a negative. So the simplified anti-diagonal is negative 580. With the general procedure of positives minus negatives, the second partial determinant is negative 414 minus negative 580, resulting to positive 166.